dear students, and welcome to today's lesson. This morning we shall be looking at a reflection of light through spherical mirror, or you can call it curved mirror. Spherical or curved mirror. In our previous lesson we also looked at a reflection but on plane mirror. And then we touched a lot of things while we were looking at that. So today we are going to be looking at the curved or spherical mirror. These are the two examples of or other types of a spherical mirror we have. You can see it is a cycle, it is spherical in shape. And so reflection also occurs here, just like it occurs on the plane mirror. But the manner of reflection here on the curved mirror and that of the plane mirror, they differ. So that is why after looking at the plane mirror, we saw the need to look at the reflection on the curved mirror. So there are two types of a curved mirror or spherical mirror. One, the concave. We can call it converging mirror. And then the second one is the convex, or you can call it diverging mirror. Of course, when we're looking at the plane mirror, I told you the difference between a mirror and a lens. This is a lens. This is a spherical lens also. And when you look at it, you see it went inside somehow. So this is a concave lens. You can see the back looks as if it is pushed out. This is the convex surface, and this is the concave surface. So this is a lens. But this is a mirror. If you look at this, you notice that the back of this looks like the surface of this, while the back of this one looks like the other side of the lens. So, again, if you look at the images, I want you to look at something now. When you look at this mirror, I want to use this marker as an object. Now, I want you to view the object in the mirror. You notice the size of the object is a little bit diminished. Now, I want you to look at the other mirror and then look at the size of the object again in the mirror. You notice the size difference between this and the former one. So the other one that produced almost the same size of the object is what we refer to as the convex mirror, while the one that produced the bigger size, the magnified size of the object, which is the last one you saw in the mirror, is what we refer to as the concave or converging mirror. Now, if I use this sphere, I draw something like this and put my principal axis, I call this place my pole. And then if I shade the outer part, whenever a spherical mirror has the outer surface shaded, leaving the inner surface to be the reflecting surface, the mirror is known as the concave mirror. But if on the contrary I have something like this, I have the inner surface. Okay, let me do this. I have something like this and have the inner surface shaded. Now, leaving the outer surface to be the reflecting part, it means I formed a convex mirror. So once the outer surface is shaded and the inner surface is the reflecting part, we have a concave mirror. And that is what we have here. This is the concave mirror. Okay, this is the concave mirror because the inner surface is what? The reflecting surface, while the outer surface is shaded. But in this case, you can see the inner surface is shaded and then the outer surface is left as the reflecting part. And so this is the convex, while this is the concave. Now, I want us to look at the different parts of the mirror. Now, for the different parts of the mirror, we have the pole. That's the different parts of the spherical mirror now. We have the pole, the center of curvature, the principal axis, the principal focus, the radius of curvature, and finally the focal length. Now, if I have this as my full sphere, I'm going to shade the part behind. and then leave this to be my reflecting surface. Now, if I shade the back of the mirror, leaving the inner surface to be the reflecting part, what it means is that I have formed a concave mirror. Now, I am going to put a straight line through the center of that circle and then cut the mirror. Now, remember the first part of the mirror says the pole. Now, the pole is the point, or let's say the midpoint of the arc that forms the mirror. This is the mirror surface. So the midpoint is my pole. I call it P. Then the second one is center of curvature. The center of curvature is the normal center, the major center of the entire spherical shape. I call it my C. That is my center of curvature. You can see what we have here. The pole is the center of the reflecting part. This is the reflecting surface. So the midpoint of the reflecting surface or arc is my pole. Then the second one says center of curvature is the center of the sphere from which the mirror takes a part. This is the sphere. And it is from this sphere that this mirror took a part. So the center of the entire sphere is my center of curvature. And that's the center of the entire sphere. Now, the third one says principal axis. Principal axis is this line that runs at the center of the sphere that cuts the reflecting surface to produce the pole. That is my principal axis. Now, the second one, the fourth one says principal focus. The principal focus is noted by capital letter F, and it is a point located just somewhere here. You have your principal focus F. Okay, we said the principal focus. Okay, the next one is what? The radius of curvature, R. The radius of curvature is the distance from pole, which is our P, to C, which is our center of curvature. So our radius of curvature is from here to this point. You have our radius of curvature. From the center of curvature to the pole is our radius of curvature. But the entire line is what we refer to as principal axis. Then the last one says focal length. The focal length is just the distance between the pole and the principal focus. I suppose says focal length is the distance from the principal focus, which is our F, to the pole, which is our P. And then when you look at the formula we have here, we say it is geometrically equal to half of the radius of curvature, because we know that radius of curvature is from the center of curvature to the pole. Since the radius of curvature is from here to here, and we are told that focal length is from here to here, which means our focal length F is equal to half of the radius of curvature. Half of what? The radius of curvature, R. And mathematically we know that this is equal to 1 over 2 times what? R, which simply gives us R over 2. And that is what we have here as the formula for the focal length. Now, having seen that, I want us to look at this particular principal focus differs from that of the concave mirror to that of the convex mirror. So let us look at it. Now, based on the principal focus, which we saw as F, capital letter F, then focal length is small letter f. Now, the principal focus of a concave mirror is quite different from the principal focus of a convex mirror. And that is the essence of these two diagrams. Now, for the first diagram, you notice that the outer surface of the mirror is polished. And so the inner surface is used as a reflecting surface. And so, when rays of light fall on the inner surface, you notice that they will all reflect. This is ray P, and this is the reflected ray P. This is ray R, and this is the reflected ray R. This is the principal axis. Then let's assume this to be ray Q. It will also reflect, and then the final ray will also, this is ray Q, and this is the reflected ray Q is this. Then the final one, let's say A, and then this is the reflected ray A. So you notice that all of them, as they fell on the surface, they all went through the principal focus. And so, because the rays of light, all of them passed through this principal focus, we say that the principal focus of a concave mirror is a real focus. That is a real principal focus. We just call it a real focus. But then, when we look at that of the convex mirror, you see the inner part of the mirror has been polished or shaded. Now, when rays of light fall on the reflecting surface, immediately they will reflect. They fall on the reflecting surface, they will reflect. They will fall on the reflecting surface, they will reflect. That's what we can see here on how many rays? 1, 2, 3, 4. This remains our principal axis. You notice that these rays of light didn't get to the principal focus, but we can produce the imaginary rays backwards into the sphere, and then we allow all of them again to meet the focus, which ordinarily they should if they had the opportunity to come inside. So when you look at that of the focus of a convex mirror, you notice that rays of light didn't get to it, unlike that of the concave. And so we refer to it as a virtual principal focus. And then it is called virtual focus. So in exam situation, you are asked, what is the difference between a ray focus and a virtual focus? A ray focus is formed on a concave mirror because of the rays of light which gets through the principal focus. But in the case of the convex, the rays of light don't get to the focus, and so that's why it is a virtual focus. Now, for us to look at the image formation principles, we notice that sometimes when images form on the convex and concave mirror, they appear in different positions. But for us to be able to study the positions of images that are formed in concave mirror, we need to look at this principle. The first case of this principle says if we have our mirror this way, we shall continue to use the concave because most images that are formed on the concave mirror are real. You can see that here, rays of light used to get to a good number of them, though there is an exception to that which we shall still see. Now, if I have my principal axis as this and my pole P, you notice that if I place an object here, you notice that a ray of light, for instance, let me use one ray of light to denote this. Of course, when an object is before a mirror, a lot of rays of light fall on the mirror from the object, but we just use one to see what happens. A ray of light will simply fall on the mirror. Now, if I have my focal length, my principal focus here, you notice that that ray of light that falls straight or in a parallel direction to the principal axis will reflect through the principal focus. Just like we have seen, this is a reflected ray. So any ray that moves from an object to the mirror will definitely reflect through the principal focus. Now, case 2 says if we have the mirror again, the concave mirror again, and the principal axis and the pole, and again we place our objects here, and then our principal focus F here. You notice that if the ray of light, for instance, didn't move straight, of course, a good number of rays will move straight to the mirror and reflect through the principal focus. Then some will again move through the principal focus and get to the mirror, and then they will reflect in parallel direction. So this is just the kind of the opposite of what we have here. If the ray moves straight to the mirror, it will definitely reflect through the through the principal focus. But if it moves through the principal focus to get to the mirror, then it will reflect in a parallel direction to the principal axis, just like it did in this case. Now, the last case, which is case 3, says if we also have our mirror in a concave manner, and then our principal axis, P, our pole, and we have an object here, it is possible that this point will be our center of curvature. So what happens is this. If a ray of light passes from the object, okay, let me shift this a little. If a ray of light passes from the object through the center of curvature to get to the mirror, what happens is that if the reflection moves this way, the incident is this way through the center of curvature, the reflection will also pass back through the center of curvature. So it is important for you to note that once an object is placed before the mirror, so many rays fall from different places. One, if the ray falls from the object straight to the mirror, it will reflect through the center of principal focus. Then, if the other rays that are moving from the principal focus to get to the mirror will reflect in a parallel direction this way to the principal axis. Then, those ones, for instance, this is our C. Those ones that may pass through the center of curvature to get to the mirror will still reflect back through the center of what? Curvature. So this is the behavior, or these are the behaviors of the rays of light that reflect from an object once it falls on a mirror, concave or convex mirror. Now look at the placement of the objects and the formation of the images, we have seen how the rays reflect from the objects to the mirror. So now, the first case says, when the object is at C, that means if the object is placed at the center of curvature, before the mirror at the center of curvature, how does the reflection occur? And then what are the characteristics of images that are going to be formed? First of all, you can see that this is our center of curvature, C. And so the object is placed at the center of curvature. Now, the first ray moved from the object and struck the mirror, then reflected through the principal focus. It reflected down. Then the second one that didn't move straight, rather moved through the principal focus. That is the ray that is representing those ones that moved through the principal focus. Reflected also down the center of curvature. So, the point of intersection of the two rays produced the image. What that means is that once an image is placed at the center of curvature, the rays must intersect downwards, and that is where the image is going to be formed. Now, you look at the characteristics of the images that are formed. One, the image again is formed at the same center of curvature where the object was placed. The image will still be formed at the same center of curvature. But this time around, the image is upended, is inverted, is upside down, as you can see. And again, one of the most important principles or property of images that are formed at the center of curvature due to the object is that the image retain their size. They don't magnify, neither do they diminish at the center of curvature when concave mirror is involved. Now, these are the properties that have already been listed out. One, it says the image is still at C. That means the image is formed at C, at the center of curvature. Two, image is real. The image is real because the intersection of the rays of light produced the image. The rays of light actually got to where the image was produced. In fact, they are the properties that produced the image. So the image is real. Now, the third one says the image is inverted. You can see the image is upside down with relation to the object. Now, the final property says image is the same size. This is because it was formed at the center of curvature. Now, the second case says when object is placed between the center of curvature and the pole. Now, this is the pole, and this is our center of curvature. So, the object is placed in between. It doesn't matter where, but it has to be between the center of curvature and the pole. Now, look at where we placed the object. You notice that the first ray moved to the surface and reflected backwards through the principal focus again. Then, the second ray that moved from the center of curvature, you can see that it went to the mirror and still reflected through the center of curvature, because we showed in the previous diagram that whatever ray passing through the center of curvature must reflect through the same center of curvature. The one passing perpendicularly or parallelly to the principal axis will reflect through the principal focus. And the one passing through the principal focus will reflect in a parallel direction to the principal axis. So, you can see the two rays we described here now. Now, when those two rays moved below the center of curvature, the principal axis, they intersected at this point. And that is where we have our image. Now, what are the characteristics of this image again? I want you to observe, one, the image here was shown to be inverted. That is in the first case. This is because the image formed below the principal axis. That is why it is inverted. Now, when you come to this case again, you notice that this is the principal axis again, and the image formed below the principal axis, so it will definitely still be inverted. Now, what are the characteristics? One, the image is magnified. This is because it has left the point of the object, has left the principal focus and moved closer to the what? Reflecting surface. And this is a concave surface, so the more it comes to the reflecting surface, the bigger it becomes. So magnification will take place. Secondly, the image is going to be real because rays of light actually were the people that produced the image. So the rays of light got to the image, and so it's going to be a real image, not the virtual image like we saw in the case of plane mirror. Now, the third case says image is inverted. This is because it is forming below the principal axis. So that's why it is inverted. And finally, the image is formed beyond C, that is beyond the center of curvature. Once you place your object between the center of curvature and the pole, the image will be formed beyond the center of curvature. Now look at case 3. Case 3 says when the object is placed at the principal focus. When the object is placed at the principal focus, that is F, a significant thing again happens, just like when the object was placed at the center of curvature C. What is that thing that happens? The image is always formed at infinity. So get this into your head, that once an object is placed at the center of curvature, the image is going to be what? The same size. But if it is placed as the principal focus, the image is going to form at infinity. How? You notice that the first ray reflected to the surface and went through the principal focus. Then the second one that passed through the center of curvature reflected again through the center of curvature. Now, if you continue to produce these two rays, they will get to infinity. And you'll follow it because they are parallel rays. So the image is produced at infinity. The reason is because the object is placed at the principal focus. So properties, number one says image is at infinity. We have seen that. Second property says image is magnified. Of course, image magnification will continue because the image has left the principal, the center of curvature and is coming closer to the reflecting surface, so it will continue to magnify. Then third one says image is real. It is real because it was formed at infinity by the parallel rays of light that continued moving downwards. Then the fourth one says image is inverted. This is because it is still below the principal axis. The image is still formed below the principal axis. Now the fourth case says when the object is beyond C, when the object is placed behind or beyond the center of curvature. I want you to look at the three rays of light that we use to show this principle. One, the ray of light moving from the object struck the mirror and reflected through the principal focus F is reflected downwards. The second one that passed through the principal focus also reflected downwards. And then the last one that passed through the center of curvature went to the reflecting surface and returned to the reflecting surface again. And returned through the same center of curvature. These were the three rays we used in the previous diagram that we used to show the behavior. So all the rays that are coming from the object, some will go straight, some will pass through the principal focus, some will pass through the center of curvature. So in whatever case they occur, this will still remain the behavior. Now, you notice that this one, as it was reflecting, passed through this point. This other one came here and reflected through this point. The last one came here and reflected backwards. And three of them met at this point. Now, this point where the three met is where the image is formed. That is where the rays of light produce the image. You notice that this image has been produced between F and C. This is F, this is C, so the image is formed at the center. Now, the properties. One, image is between F and C, just like we have mentioned. Secondly, image is real. It is real because the rays of light produced it. Third one, the image is inverted. It is below the what? The principal axis. So it's going to be inverted. And lastly, the image is what? Diminished. The image is diminished. You can see that because it was formed closely in between F and C. Even though we know it is moving down again to the reflecting surface. Now, I want us to look at the place where we have the exception we said in every rule. There will definitely be an exception. You have seen that the other four cases we looked at, the image is always real and always inverted. Real because the rays of light gets to them, inverted because they are always below the principal axis. But let us look at the fifth case, for instance. The fifth case, we have the object when object is placed between the principal focus and the pole. Now this is the pole, and this is our principal focus. And we place the object between. Now this is our object X. Now what happens? The ray moving from the object struck the mirror and reflected through the normal line and went down. Now, the other one that went through the center of curvature returned through the center of curvature. And now, you notice that because this is a concave or converging mirror, the rays behind, the imaginary rays behind are going to converge at a point. When you continue to produce them, they will converge at a point. Now, wherever the convergence takes place, wherever the convergence takes place, that is where the image is going to be formed. Now, remember this is our principal axis. And now the image was formed not only behind the mirror, but above the principal axis. I told you, once the image is formed below the principal axis, it must be what? Inverted. It must be inverted. But now it has formed above the principal axis, so the image is definitely going to be erect. Again, you can see that we only produce the imaginary rays until it converges.